So continuing the discussion on free surface flows, let's take a look at another problem which we see almost daily. This is the shape of a falling jet. So what I'm showing you here are two images. On the left image you can see that when you open the tap, the water actually the jet of water that comes down thins down as it falls. And the first guess that most of you can make is that it thins down because gravity is pulling it down. But at the same time, the radius of the jet is changing and therefore the curvature of the jet is also changing. We will basically determine the shape of this jet because of the following forces: inertia, surface tension and gravity. Now if you let this jet to continue to fall down, then one of the common things that you see is that this jet breaks up into tiny droplets. We've already seen this in the introductory video. This is called the Rayleigh-Plateau instability. This is not the subject of this particular lecture, but we will rather focus on the first part, which is the shape of a falling jet. So let's consider a simple jet that we see in our day-to-day life. So I'll make a simple sketch of this jet. So here's, let's say, a small tap. The radius of this tap is R0, and our goal is to determine the shape of this jet. Now before we proceed further, let's find out what are the dominant forces in this problem. And to do this, I've taken a simple example. I've made some back of the envelope calculations to determine what are the dominant forces. So let's consider a tap. This is just an example. A tap whose radius is about 5 millimeters. So that gives me 5 into 10 power minus 3 meters. We will consider a velocity, that is exit velocity of the fluid, is about 0.2 meters per second. We will take fluid as water. Therefore, its kinematic viscosity is 10 power minus 6 meters square per second. Now let's first calculate the flow rate. Flow rate Q is pi r square, the cross-sectional area, times the velocity. That's velocity is 0.2 meters per second, and this comes out to be about 5 pi into 10 power minus 6 meter cube per second, or it's 5 pi into 10 power minus 3 liters per second. This is 0.016 liters per second. Okay, what does this flow rate mean? If we were to fill one liter bottle, then time taken will be, let's call the time taken to be t, and this will be 0.016 seconds, and that's approximately 62 seconds. So it roughly takes a minute to fill a water bottle of 1 liter capacity at this flow rate. This is sort of the common experience when we use a typical UV or an RO filter. And I specifically mention those kinds of filters because those kinds of water sources, because what we're seeing here is a thin glassy jet. But if you use much higher flow rates, then you have aerators in our kitchen and bathroom fittings, and you have aerators. Because of that, you have a lot of turbulent flow, and this is not really applicable. So I'm making the problem analytically tractable by taking a very simple problem where only a few forces are relevant. So hopefully I've convinced you that these numbers of radius and velocity are reasonable. Let's calculate the Reynolds number. We know that Reynolds number will be the ratio of inertia to viscous forces, and I've defined the Reynolds number to be velocity u times r naught by kinematic viscosity nu, and this turns out to be 0.2 into 5 into 10 power minus 3 divided by 10 power minus 6, and this is 10 power 3. So the Reynolds number is 1000. So you can see that even at such fairly low flow rates, which means that if you take a water bottle, it takes a minute to fill it, even at such low flow rates, the Reynolds number is a factor of close to 1000. So which means that you can safely assume that such flows are inertia dominated and you can ignore viscous forces at leading order. So we will consider this problem completely devoid of any viscous forces. Okay. So what's the goal? The goal is to determine the shape of the jet. That is, what we want to do is, I want to determine if the radius r of z at any location. So the goal is to determine r of z. Okay, so how do we set out to do this? So what are the things that we know? We know that the forces at play are inertia, surface tension, and gravity. So if you have three forces that are at play in the problem, you can expect that you'll have two non-dimensional groups. We will see how these non-dimensional groups naturally emerge in the analysis. So I can think of a non-dimensional group from inertia to surface tension balance, or a non-dimensional group involving a balance of inertia to gravity. Okay. And since viscous forces are not present, we can apply Bernoulli's equation. So how do we do this? Let's consider a small control section or a control volume. So here's my jet. Let's define a coordinate system with z going downwards. We have also said at the beginning that the radius of the jet, we'll call the radius r0 to be the radius at the inlet, and the radius at any location will be r of z. We have gravity going downwards. We'll also say that this is a passive gas, just like what we had done in earlier cases. It's a free surface flow. So the outside pressure can be P0 or P infinity. So let's call it P0. Let's consider a small control volume. I'm trying to show this control volume using a dashed red boundary. This is my control volume. And what's this height of this control volume? This control volume is of height z. So z equals 0 means you are at the opening of this tap, and at any given z you basically descend downwards. We will also consider two locations. So we'll say this location A, this is at z equals 0. And we'll consider another location B at some arbitrary z. Okay. Now let's apply the Bernoulli's equation. Between these 2 points A and B. And what do we get? Pressure. We know that pressure, what is Bernoulli's equation? Bernoulli's equation, for those who may not be familiar with or forgotten, P plus half rho U square plus rho GZ will be constant. That's the Bernoulli's equation, right? So let's apply across these 2 points. It's PA plus half rho UA square plus rho GZ will be PB plus half rho UB square, right? We also know that the pressure inside the jet minus pressure outside the jet is gamma times curvature, which is gamma times 1 by R1 plus 1 by R2. What are these 1 by R1 and 1 by R2? If I take any arbitrary portion of the jet, then there are two radii of curvatures. There's one radius of curvature which is inside the jet, inside the liquid. So this would be, we'll call this as R1. There is another one which is taken outside. This we'll say is R2. That's the radius of, I'm showing you the radius of curvature. Therefore, you have two radii of curvature, but they are on different sides. Typically, R2 is much larger than R1, and that's also evident in this image. You can see that the radius of the jet itself is very thin compared to the outer radius of curvature, which determines how this jet is actually thinning down. So this immediately means 1 by R2 is much smaller than 1 by R1. So I can now conclude that the pressure inside minus pressure outside is approximately gamma by R1. Alright? And therefore I have at A, if I apply this relation, the pressure inside will be PA, the pressure outside is P0, and this will be equal to gamma by R0. And therefore I have the pressure at the location A will be P0 plus gamma by R0. Okay. Note that the pressure here is only a dynamic pressure, the local because of dynamics. The hydrostatic part need not be considered here because in the Bernoulli's equation I've already taken that into account with this extra term rho gz. At B, the same expression gives me PB minus P0 will be gamma by, I do not know the radius, therefore I'll call it at R at Z. And this gives me PB will be P0 plus gamma by R of Z. Right? So now I've got PA and PB. And therefore I know PA minus PB in the Bernoulli's equation. Let's give this Bernoulli's equation a label. Let's call this as equation 1. We'll call these equations 2 and 3. So now I can use equations 2 and 3 and substitute them into equation 1. And what do I get? Let's do that carefully. Substituting 2 and 3 into 1. PA, that will be P naught by gamma by R naught plus half rho U naught square. What is U naught for me? U naught is the velocity of the inlet. That's my velocity U naught. Half rho U naught square plus rho GZ will be equal to P naught plus gamma by R of Z half rho U of Z whole square. I do not know the velocity at B. So U of Z is the unknown velocity at B, right? And this gives me half rho U naught square. I can cancel out, here I've already cancelled out P naught on both sides. Half rho U naught square plus rho GZ plus gamma by R naught is equal to half rho U of Z whole square plus gamma by R of Z. Gamma is my surface tension. What do I know in this relation? I know U naught, I know R naught, I know the density of the fluid, I know the value of gravity. What is unknown here? I do not know R of Z, that's the radius of the jet at any arbitrary location Z. I also don't know its velocity. We can rearrange this and as U of Z by U naught. I get U of Z by U naught. This is a straightforward algebra. I get half 1 plus 2 GZ by U naught square plus 2 gamma by rho U square R naught times 1 minus R naught by R of Z whole power half. This is an important relation. We'll call this as relation 4. This equation relates the velocity of the jet at an arbitrary location Z in terms of the radius at that location, which is R of Z. Alright. So notice that when we do this analysis, I said we have three forces, and so therefore you should expect two non-dimensional groups. Now two non-dimensional groups emerge in this analysis. How do they emerge in this analysis? If you notice the first term here, I am underlining this here. You have gravity at the top and I have a velocity square, which is an indication of inertia, and I have another number here, 2 gamma by rho U0 square R naught. So we can now define two non-dimensional numbers. Define this number, we'll call it as FR, which is U0 square by G times R naught. Gravity is in the denominator and velocity is in the numerator. This number is called the Froude number, and it's a ratio of inertia to gravity. Why have I chosen inertia to gravity? Not because you see the combination here in the expression 4. I have this expression g there in the numerator and u0 square in the denominator. So this number naturally sort of emerges. I define another parameter, a non-dimensional number called we, which is rho u0 square r naught by gamma. This number is called the Weber number, which is the ratio of inertia to surface tension. So once I have these relationships, these non-dimensional numbers, I can substitute into my equation, and what do I get? We get u of z divided by u naught will be 1 plus 2 by Froude number. I have to multiply and divide by r naught. I get z by r naught. The other number is 2 by Weber number times 1 minus r of z. Whole power half. Okay. We'll call this relationship number 5. Now, to get velocity at any arbitrary location, I need to know the radius at that location. But which means that I need another relationship. So what have we not used? We have applied the Bernoulli's equation, which either comes from the mass, momentum, or the energy equation. We still haven't used one more important equation, which is the mass balance. Now we will apply the mass balance. It's a fairly straightforward relationship. It says that the mass flow rate coming at the inlet should be equal to the mass flow rate of the outlet for the control volume. We are ignoring effects such as evaporation, which means that if you look at this control volume, the fluid is traveling tangential to the interface. There is no loss from the sides. There is fluid coming in at the inlet where the radius is r0 and the velocity is u0. The same fluid is leaving at the exit where the radius is r of z and the velocity is u of z. And therefore, I can now simply apply this mass balance to get density times pi r naught square u naught is equal to density times pi r of z whole square times u of z. This can be either mass flow rate or volume flow rate. They are equivalent because it's an incompressible flow. And therefore I have r of z by r naught will be u naught by u of z whole power half. Correct? And so I can now, this can also be written as u of z by u naught whole power minus half. From this I get a relationship between the ratio of the velocities as r of z minus 2. So let's now substitute this into the equation. What do I have here? Wherever there's u naught by uz by u naught, I can substitute r of z by r naught. Let's do that. We'll call this as equation number 6. Using 5 and 6, what do we now have? We have r of z by r naught whole power minus 2 is 1 plus 2 by fr z by r naught plus 2 by Weber number r naught by r of z whole power half. And therefore I now have a simple expression for r of z. Well, we'll just see that it's not so simple. R of z by r naught will be 1 plus 2 by fruit number z by r naught, 2 by Weber number 1 minus r naught by r of z whole power minus 1 by 4. Right? We can make some simplifications further. If you see this expression, this has basically expressions involving r of z on the left hand side and right hand side. We'll still give this a label before we simplify it. Let's call this as relation number 7. Okay. Now I can take the fourth power on the left hand side. I get r of z by r naught power minus 4 will be this expression here. R of z, and this implies r naught by r of z power 4 will be now we can multiply throughout by r of z to the power of 4 to get a relationship in the following manner. We get an expression of the form r of z power 4 multiplied by 1 plus 2 by r naught, 2 by fruit number z by r naught plus 2 by Weber number. This is the first term, fourth power. Then I have a cubic term which is minus 2 r naught by Weber number, which is r of z cube, and then I have r naught power 4 is equal to 0. So let's call this as a of z, let's call it as b, let's call it as c, which also c also includes the negative sign, and this simply we get a of z times r of z power 4 plus b times r of z cube plus c is equal to 0. We get a simple quartic equation for the radius of the jet at any location. Now at every z location, if you know the Weber number and if you know the Reynolds number and the fruit number, because remember Weber number and the fruit number are completely described by the initial conditions, which is R naught and the U naught, and of course the material properties of the fluid, then at any z location what you get is a simple quartic equation, which means that R at that location will have 4 roots and you should only take the positive root. So one can actually solve this problem, and we can say that we have now come up with an expression for the radius of the jet at any arbitrary location. We can stop it here. But let's go one step further, and rather than trying to get the exact solutions at every z, we will basically look for a simplified analysis. Rather than trying to get the exact solutions. Let us get some approximate solutions. I will show you one example of how to get an approximate solution. So let's consider Weber number very large limit, which means that inertia is much larger than surface tension, and therefore you should expect that in that limit surface tension will cease to be important, and now you have a balance of only pressure, inertia and gravity. So gravity is the driving force which is pulling it down, and that causes an acceleration and generates inertia in the system. So if we do this, now since Weber number is large, this automatically means 1 by Weber number is very small, basically goes to 0. And now I have we get A prime of Z, R of Z power 4, and remember B goes like minus 2 by Weber number times R naught, but because 1 by Weber number goes to 0, B goes to 0, I have just plus C. Okay, and C does not involve any Weber number. I call it A prime of Z because A prime is different from A of Z in that the Weber number term that I am highlighting here, the Weber number term in this disappears. Okay, so A prime would be 1 plus 2 by root number into Z by R naught. Okay, and therefore I have R of Z power 4 is minus C by A prime of Z, and R of Z is minus C by A prime power 1 by 4. Let's substitute the expressions for C and A prime. C would be minus R naught, so this becomes minus C becomes plus R naught power 4, and the denominator is 1 plus 2 by root number Z by R naught power 1 by 4. And now I have R of Z by R naught is approximately 1 plus 2 by root number Z by R naught power minus 1 by 4. So in other words, as you go down, as Z is increasing, the radius of the jet is thinning in the form Z power minus 1 by 4. Okay, one can also calculate the velocity. In the same limit, U of Z by U naught, we have already seen is nothing but R of Z by R naught power minus 2. So the ratio of the velocities would be 1 plus 2 by root number into Z by R naught power plus half. Okay, so as you go down, as Z increases, the velocity is increasing with Z, but it increases as Z power half. This is expected because you have gravitational force which is in an accelerating frame. Therefore, the fluid basically accelerates as it goes down. But in the process, because of mass balance, the fluid has to thin down. I will leave it to all of you to try out the other case of a fluid number going to infinity limit, but we will take a look at it in a tutorial session during the course. Thank you.